Good afternoon, everyone. So we're going to start a new topic today that different than regression. So until now, we've focused on regression as a way of covering some of the basics in machine learning, concepts like cross-validation and regularization, overfitting, underfitting, maximum likelihood. And now we're going to kind of switch gears, look at a different application, different task, and see that we can apply all those same ideas again. So in this unit, our data set is going to be this Wisconsin breast cancer data set. So the idea here is that to diagnose breast cancer, the common thing you do is you take a tissue sample, and then an expert looks at that. They stain the sample and they look at it in a microscope, and just visually they look at, they quantify various things about what they see, and they additionally try to determine whether it's malignant or benign. But there's a more robust way of determining whether it's malignant or benign, which is through a biopsy. So, but still, we might wonder, can we take all the statistics that are computed from these images? So here's an example of some of them in the data set. I don't know what all these mean, but they're things that you can see from you can get from the slides, and then they end up putting a 1 through 10 rating on each one. So the question is, from those features, there's a total of 9 of them, can we predict whether the patient has malignant or benign cancer? And in this data set, we do have ground truth label for that. So for whatever reason, it was coded 2 for benign and 4 for malignant, but what we call the class, or this outcome, this binary outcome, takes on only those 2 values. So the question then is, can we use these first ones to predict the last one? So that's the objective. There's 683 samples in this data set, so it's relatively small, pretty common in machine learning classes. So usually the first thing we like to do whenever we get a new data set, we like to visualize it somehow. So this data set, because all of the features are discrete, they're integers 1 through 10, we cannot plot our usual scatter plot. So this is just looking at 2 features, this margin and size unif. So if we tried to do a scatter plot here, the problem is that all the dots would line up exactly on each other, and we could not see which of these combinations is more likely to be malignant or benign. So what we're going to do instead is we're going to use the number of malignant or benign samples. So number of benign is going to be, so benign is going to be green, malignant is red, but if you have multiple benign samples all showing up with this feature combination, you're just going to get a bigger circle. Okay, so what you see here is, if given these 2 features, as you move in this direction, most of the samples are red. As you move in this direction, samples down here are green, which tells us that as these quantities get smaller, there's a larger chance of this being benign. And here we're just using the size of the dots to get around the fact that the features are on this grid. Making sense so far? Okay. So the question then is, in this case, how could we classify a test feature? So this leads us to the generic problem of binary classification. And just to state it, in the general case, we're given training data of the same form that we tend to see. We have some feature vectors of dimension d. We have scalar labels. But now the labels, we're going to say they come from either 1 or minus 1. There's nothing really that special about 1 and minus 1. It leads to some notational simplifications later. But another common target could be, or common set of targets could be 0, 1. Or we saw in the data set for some reason they use 2, 4. So it's not really that important how you code it until you get to some derivations, and then some are easier than others. But the point is that there's 2 values for the targets, and essentially you can think of it as categorical. There's just 2 categories for the targets. It's not like one is bigger or smaller than the other, they're just different. So this is the first time we've seen categorical targets. And we call these 2 target values the classes. And we'd like to, when we try to predict the class of a feature vector, we call that classification. So there's a myriad of applications for this. We talked about this problem of, like, are these cells cancerous or not? Another one is, if you're given a picture like this, you might want to say, is that a weed or a crop? By the way, what would the number of features be in this case here? The number of pixels. Yeah, you can think of each, this image is like a grid of many different pixels. Each pixel actually has a red, green, blue RGB values. So it's really, you could say you have like many pixels times 3, because you have basically a red picture, a blue picture, and a green picture. We'll talk about images in a couple units. Okay, so mathematically we would like to design what we call a classifier, which is some function, we'll just call it f, that takes in the features x and produces an output, y hat, which is either going to be 1 or minus 1. It's never any other value. It's just those are the 2 possible values. And we would like that the y hat that we put out matches the true label y with high probability. That's the usual outcome. It would be great if it always happens, but it's not usually the case in practice. Okay, so that's our objective. That's our classifier. Now, something we can do in this case that we couldn't do previously when we studied regression is we can think about decision regions. So, like here in the picture on the right, what we're showing here is this is feature 1, feature 2, and all these light colored dots are examples of targets for those particular feature combinations, and then these ones are, maybe these targets are 0. Actually, sorry, let's call these minus 1. Let's call these plus 1. Okay, so we have examples of the plus 1s and the minus 1s. When we think about designing this classifier, we can think of designing some sort of curve that separates the space into 2 regions. So if this is our classifier, then anything on this side we are classifying as a minus 1, and any point over here would be classified as a plus 1. Okay, so we have this concept of a decision region. This is the decision region corresponding to minus 1, and that's the decision region corresponding to plus 1. And we could define the decision regions like this. So this says, so this curly brace means the set. So this is the set of x such that f of x is minus 1. This is the set of x such that f of x is plus 1. So this is, let's say, r minus 1, r plus 1. So let me erase this. That's really what we have. Okay, any questions so far? All right. Okay, so there's many, many ways to do classification. But we're going to study kind of the simplest, most common in some sense, called binary linear classification. And we can think about this as a 2-step process. Step 1, you compute what's known as a score, or sometimes a discriminant. this way. So this formula looks very much like regression, right? Linear regression. So it turns out that our parameters, we're going to call them B and WJ now. So previously we called them beta, beta 0, beta 1, beta 2. It's just a change notation. Otherwise, it's identical in terms of the what it means. But it just turns out if you look around in a lot of the classification literature, they use B and W. So I'm just being consistent with that. But conceptually, it's the same thing as using betas. Okay. So here we have our features. X, we're multiplying by these slope coefficients. We're adding an intercept. And we're getting this intermediate quantity, which is called the score. That's just like what we did in regression, but in regression, we would stop there. We'd be done. Now, in the second step, we threshold that score. And so if the score is 0 or greater, we assign the output equal to 1. Otherwise, if the score is less than 0, we assign the output as -1. Okay, so it's kind of like a two-step process where you do some sort of linear regression to get this intermediate score, and then you do some thresholding or quantization to get your final discrete output. Okay, so that's binary linear classification, and we're going to focus on that pretty much this entire unit, just studying it, and even in a following unit, we'll focus on this as well. Okay, so as usual, our parameters, in this case W, we can put them in a vector, intercept B. We're going to learn these from the training data. And the whole question for today is how do we do that? Okay, any questions so far? Yeah.
If you have one classifier, can you only identify 2 things?
So, yeah, I think you're asking if the target can have more than 2 possibilities?
Yeah.
Yeah, that's a great question. We're going to talk about that on Wednesday. Today, we're going to focus on the binary case, and binary means 2 things, and then later we'll do multinomial, so you have 2 or more. Okay, any other questions? Okay, so let's notice a few things just geometrically or visually about what we have in this binary linear classification case. So imagine that I'm right on the border between deciding whether to output a 1 or a -1. That would mean if I'm at z equals 0, that's exactly on the border, right? I happen to assign that to 1, but that was just sort of arbitrary. Maybe I could have assigned it to -1. The point is when you're right on that boundary, you really don't have a good idea of how to classify it. So that would mean that z is 0. And so when we set this to 0, you get this equation. So this is the equation for what we call the decision boundary, the boundary between outputting a 1 or a -1. And we can visualize that as the set of all x, because here we're making plots in the x domain, the set of all x such that b plus x transpose w is 0. Okay, so if you think about it, this is going to give us, this is the equation for a line in d dimensions, or here in these pictures, it's a line in 2 dimensions. So we call this a hyperplane. It's basically like the generalization of a plane. If we were in 3 dimensions, it would be a 2-dimensional plane. Since we're in 2 dimensions, this is a 1-dimensional line. In higher dimensions, it would be some higher dimensional plane. But it's basically, we're talking about this thing here. Okay, so essentially, when we do this binary linear classification, the linearity is really coming from 2 places. First, you can see that it's a linear, it's about the score, and the score is linear in the parameters. Right? So if I change any of those parameters, you'd see a linear change in z, or if you changed x for fixed parameters, you'd also see a linear change in z. And this linearity in x is what causes the decision boundary to be a line. If somehow you, let's say, put a square on these x's, then what you would find is this would no longer be a line, it would be some sort of curve. But because it's linear in X, this boundary is linear. So I'll just make a little note here. This is a linear decision boundary. Okay, and so that's going to have some big consequences for the kind of data sets we can handle. So, for this to work well, we would like that our data set is such that you can somehow find a line for which all the samples from one class on one side and all the samples from the other class are on the other side. In practice, that's probably not going to happen. So here's just one example of a class where you have some overlap. There's no way that I can put a line anywhere to get perfect separation, but here, this is probably a pretty good place for where to put that decision boundary. Okay. All right, so everybody good with linear classification? Okay, let's talk a little bit more about that, the separability. So as we've been talking about, when a data set is linearly separable, so this is something about the data set. The data set is linearly separable. It means that there exists some hyperplane that separates the samples according to their class perfectly. So on the previous page, we saw an example of linear separability here, and this is not linear separability. We cannot find any kind of line where everything is perfectly separated into the two classes. Okay, so here's another picture, and what you can notice is that almost always when you have a linearly separable data set, there's actually going to be many different ways to separate it. Like here, for this data set, the blue line works, the red line also works, right? Both of them separate the data. So usually this separating hyperplane is not unique. Okay, all right, good so far? Okay, so in practice, we would really like for our data to be linearly separable because then everything works perfectly, but in practice, it's probably not going to be linearly separable, but we hope it's near to it. Okay, so as we said, in practice, most data sets are not linearly separable. And actually, there's many reasons why that could be the case. So here we have like a situation where there's just a lot of overlap. Here we have a situation where not too much overlap, but there is a little bit of overlap here. This one is linearly separable. And this one, it's separable, but not linearly separable, right? You can draw some kind of curve that perfectly separates those samples, and it's a pretty smooth curve. But you can see that it's not, I can't do that with a line. So you might say, well, okay, linear classification seems to be kind of primitive, kind of weak, and it's a lot like linear regression where that's true to a certain extent, but if you allow some sort of nonlinear feature preprocessing, you can make it very sophisticated. So here's just like a simple example of this case. Let's say I can preprocess my features. I have x1 and x2, and I just create a new feature. I'll call it x prime, which is the square root of x1 squared plus x2 squared. So if the origin is right in the center of that circle, my new feature is just going to tell me how far any of these samples are from the origin. And now you can see that if I just work in that new feature alone, that is enough to perfectly separate the green points from the blue points because there's just one radius that I need to separate them. So this is just a simple example of how it's possible to do some sort of nonlinear preprocessing followed by linear classification that could be really powerful. And it turns out when you look at all the state-of-the-art neural networks that are being used for classification, essentially you can say that the last layer is linear, but then everything up to that point is doing some sort of feature preprocessing that finally makes that linear classifier work really well. So in this sense, this is a linear classification as a building block, and it's not only in neural networks, but a lot of other approaches use it as a building block. Okay, so that's sort of linear classification in a nutshell. Feature transformations are always going to be a possibility, but we're not going to talk about them a lot for now. We're going to focus on the classification aspect for now. Okay, any questions? All right. So we learned about least squares linear regression. So you might say, well, why don't I just use that approach here? What's wrong with least squares linear regression? We could certainly set up a problem. In fact, like this is our RSS that we minimize for linear regression. And what we could do is we could just plug in for y the training labels, which are 1 and -1. We plug in our features, into A with the column of 1s in the front. And previously we called these betas, now we call them B and W, but we could do a least squares fit to this parameter vector. And how would that work? So here's a couple examples. So this is a one-dimensional case. So we have just one feature, x, and this is our target, y. And for this data set, you can see it's a very simple data set. There's 8 samples. All of these samples here have y equals -1. All these samples here, y equals +1. And so if we fit least squares linear regression, what we would get is we would get this prediction. We used to call it y hat, but now we're going to call it z. Or here it says z hat, but basically it's like our z. So that's our linear function of x. You could say it's like b plus w x for the least squares b and w. And then once we have that z, for the second step in the process, we just quantize it. So whenever z is positive, we output 1. Whenever z is negative, we output -1. So that's what the green line shows. Here's 0. So whenever the z curve is above 0, we output 1. Whenever it's below 0, we output -1. And you can see that in this case, at least on the training data, it looks like we are making perfect predictions. And if you sort of imagine test data, maybe there's a test data point over here, everything would be classified perfectly, right? It's doing just what we would expect. So it seems like everything's fine. Is everybody okay with the analogy? Does everybody see how we could think about this as regression followed by quantization? Okay, now let's change the data set just a tiny bit. We're going to take this point here, and we're going to move it out over here. So conceptually, you could almost say that these edge points should be the easiest to classify. As you get towards the center, as you get towards this x, that's where it's more difficult because, right around this point, everything changes. So this is these are the easiest samples. They're the furthest out. So by making this sample here even further out, it seems like I should not be harming anything. I'm not really making the problem any more difficult. But you can see what happens with least squares linear regression. Now what it's going to try to do is it's minimizing the sum of these squared errors. And so in order to do that, it puts the regression line here. And now when we follow it with the thresholding, whenever this crosses 0, that's when we output a 1, otherwise we output a 0. And now you can see that it's even making errors on the training set. And if I had a sample somewhere over anywhere from here to here, it would make an error. So something is going wrong. So roughly speaking, we're going to call this imbalanced case. When your data is sort of imbalanced in that, these labels are kind of tightly packed together, and then these labels are sort of spread far apart, or features. These features are close, these features are far. Least squares linear regression does not do the right thing. Somehow it messes up. So the question is, what's the solution? What's causing this behavior? The reason why is that this RSS, it's not the right loss function for this classification problem. In the last lecture, we learned that RSS is the right thing to do when you have a linear model with additive Gaussian noise, zero mean, but that's not what's going on here. We don't have that at all. We have something very different. And if you use RSS to do your training, you get really bad results. So we have to revisit this loss function. How can we come up with a loss function that will work better for this application? Okay. Is everybody good so far? All right. We can also look at what happens with our breast cancer demo. Here again, we're just looking at two of the features. And if we're doing linear classification just as a human by eye, we had to place a line here for some sort of boundary. I would probably place a line, I don't know, somewhere around here, because I have a lot of green here and a lot of red here. But as you can see, when we use least squares, least squares places the decision boundary here. And as you can see, there's a lot of red points here that are going to get misclassified. So here again, the reason why is because the green points are clustered tightly together and the red are spread out. And this is just another example of that imbalance. Here we're seeing it in 2D. Previously, we saw it in 1D. Here's a little bit more detail about how you can think of the equation for this line, in case it helps. So remember that the decision boundary is given by the set of vectors x such that b plus x transpose w equals 0. In this case, x transpose we can think about as like x1, x2. W, that w vector, we can think about it as b, w1, w2. Actually, sorry, there's one more. Sorry, I already have the B. So let me get rid of the B here. Okay. Okay, so when you do that multiplication, you get x1 times w1 plus x2 times w2. And then if you rearrange that equation and isolate x2 on one side, you can get the other side to be a function of all the other parameters. And here you can see that the equation for this line, which this is going to be x2 versus x1, is given by this. So you have an intercept, you have a slope, which is negative, and you have versus x1. So just sort of, in case you're wondering, like, how do you go from this model to these lines? It's just a simple algebraic manipulation. Okay, so again, minimizing RSS does not work too well for linear classification. So we have to come up with a different approach. Everybody good so far? All right. Okay, so again, we're focusing on linear classification, two-step process. First, compute the score from the features, intercept weights, and then threshold the score to get our final output y hat, which is either going to be 1 or minus 1. So the key question now, how do we design the parameters b and w from our training data? We saw that minimizing RSS is not a good approach. So here's the main idea. Given the score z, we're going to model the true label as a random variable. And there's many different ways to do this. The most popular model looks like this. So, and this is illustrated in this picture. So this would be z. So it says, for a given value of z, the probability that y equals 1 is this, and which is illustrated here. This is called a sigmoid. And the probability that y equals minus 1 is just going to be 1 minus this shape, which ends up looking like this. So again, we're thinking now of the true y as a random variable. That's why you can think about it probabilistically. And we're thinking about it as some function of this intermediate z here. So we have our intermediate z that is a function of our features and our true weights and intercept. And then given that intermediate z, the probability that y equals 1, it's like a coin flip, but the probability as z gets higher, the probability of getting a 1 gets very large. As z tends to infinity, probability converges to 1. Z goes to minus infinity, the probability converges to 0. And when you're at z equals 0, right there at that boundary, probability of y equals 1 is 1/2. Probability of y equals minus 1 is 1/2. Okay, so this is it's a different sort of probabilistic model than we saw in the last unit. If you remember in the last unit, I'll write it here. The probabilistic model that we used was y, the true y, equals z plus epsilon, where epsilon was noise with mean 0, let's say variance sigma squared. Okay, this was also a probabilistic model. So in that case, you'd see the probability of y given z is Gaussian with a mean of z and a variance of sigma squared. Okay, now we're saying it's a different probabilistic model. It has this shape, very different, but both of them are probabilistic models. In that sense, it's just different options. Is that making sense? Can someone ask a question if not? And if you feel like you have a question, probably someone else has the same question, so don't be shy. This is sort of an important point, and it's maybe not so easy to get the first time. Yeah.
Is the function that we're using here for classification should always have linear features? It cannot be a polynomial feature.
Yeah, we are focusing right now on linear classification. So that means that we have a two-step process where we are linear in these features and also linear in these weights. That gives us our z. And then the new thing, trying to understand, is we have this probabilistic model for y given z. So it wouldn't be too much work to do some pre-processing of our x's, and we could just replace those x's in there with polynomial versions of x. It wouldn't really change anything we're doing here, right? It's definitely possible. We're not doing that, we're just doing the simpler thing, which is this, just to be simpler, but we could do that if we wanted. Okay, but the harder thing, I think, is just understanding this. Is this sort of making it clear? So we have this intermediate variable. So this is our true model. We're assuming that there's some true parameters, b and w, such that when you plug in the features, training or test features, you get some intermediate true z's, and then there is randomness in going from z to y, but this is how you describe that randomness. Back in the last unit, you had something similar. We wrote it with beta 0 and beta vector. That gave us our true z's. But then, to get our random y, we added Gaussian noise, zero mean. So that was similar in terms of being a probabilistic model, but differing in the details. Okay, so, well, I don't want to pause too long here. It's important, but if nobody has any questions, I can certainly move on. So, so just a few things. So for this to be a valid probabilistic model, since there's only two possibilities for y, either it's 1 or minus 1, if I fix z, then the probability that it's either 1 or minus 1, if you add those two probabilities, it has to add up to 1, right? That's required. So this expression must be 1 minus this expression. See, and you can verify that that's the case. Okay, as we talked about before, this is a picture of this model here. So as z gets larger, it's more likely that the true label equals 1. When z is 0, it's equally likely that it's 1 or minus 1. That's the hardest case, really, to process. Sometimes this is written in a slightly different way to get rid of the two exponentials. You multiply the top and the bottom by e to the power minus z, and then you rewrite it as like this. So what's happening is you have a minus e down here. Okay, so sometimes people write it like this, sometimes they write it like this. But in any case, this is what's typically called the sigmoid, or sometimes the logistic function. Okay, so this is probability that y equals 1 given z. So now that we have that model, we can do a lot of the same things we did last time, like maximum likelihood and all that. Let's spend a little bit more time looking at this model. So the model that we have from the previous page, it's writing the probability of y in terms of that intermediate variable z, the score. But what we really maybe care about is what's the probability of y given the features x. So for that, the features, as we know, they get multiplied by w and shifted by b to get z. So let's try to understand the role of the b and the w and so on here. And let's look at the simplest case. We have just a single scalar feature x. So in this case, z is b plus wx. But in fact, we're going to make it even easier, and we're just going to assume that b is 0. So in that case, z is just wx. So we'd like to understand, how does this probability of y equals 1 given x behave as we change w? Okay, so when w is 1, then we're back to the picture on the previous page. Here's our sigmoid function. Here we're plotting as x goes from minus 10 to 10. You can see it transitions from 0 to 1. Now what happens if I make w smaller, like 0.5? So in that case, to get the same shape, I would have to move x twice as far to get the same z, right? So what happens is everything gets stretched out horizontally. So this is what happens when w is 5. On the other hand, what if I make w is 10? So now, very small changes in x have a big effect on z. And so you can see we get a very sharp transition. It still has a sigmoid shape, but it's very sharp transition. Finally, what if I make w minus 1? So now I'm just changing the sign on w. Now you can see the transition has changed signs. It goes from 1 to minus 1 1 to 0 rather than 0 to 1. Okay, so what we see finally is the sign of w determines whether this function is increasing or decreasing. The magnitude of w determines the sharpness of the transition. But so far, the transition in all these cases is centered at 0. Okay, so it turns out the role of b is to shift it away from 0. So let's think about what happens for more general b, any b. So now we have, previously we had this case, now we have this case. We can rewrite this a little bit easier like this. So now we have w times something. And that something you can see we're basically translating x. So to get the same behavior as before, you would have to make x minus b over w. That's where the transition will happen. So at that point, that will make z equal 0. So you're gonna have one of these curves, but then you're gonna shift it over to the right or left depending on that quantity. Okay, so this is how the parameters finally affect our model. Z is going to be it's going to depend on all of our x's, using this logistic sigma, but the intercept results in a shift. The scaling coefficients w, they determine the sharpness. And that's how it behaves in the end. All right. Okay, any questions so far? All right. Okay, so now we have everything we need to do maximum likelihood estimation. So our goal here, we have some training data, X, Y pairs, our model parameters, B and W. We want to fit our model. We have a probabilistic model. In other words, we have our likelihood function, which is the probability of Y given training labels Y, given training features X, and our parameters. When we think of Y and X as fixed and the parameters as variable, that's when this becomes a likelihood function. And we want to adjust the parameters to maximize the value of that function, maximum likelihood. And so we saw last time, so we start by saying maximize the likelihood over B and W. Equivalently, we can maximize the log likelihood because often that results in simplifications, or we could also minimize the negative log likelihood. And so that's basically this turn the crank procedure. All we have to do next is work through some of the algebra to figure out how to do that. And just to remember how we applied this last time, we had a particular likelihood, which we got with this linear Gaussian model. So the training labels Y were some matrix A times our parameters beta. A was made from our features. And we have, this is Gaussian with noise variance sigma squared. So we saw that when you take the negative log of this Gaussian, you get a quadratic plus a constant in beta. So if you want to minimize this, that's just basically minimizing this quadratic, which is also known as least squares fitting. So everything is the same now. It's just that we're not using this likelihood. We're going to use the likelihood that comes from our probabilistic model here. But otherwise, the process is the same. Okay, everybody good with maximum likelihood, the high level? Okay, so let's do the derivation then for maximum likelihood estimation for what's called logistic regression, which is this approach where we use linear regression and we add that sigmoidal conditional probability. So let's just remember what we have. So this is one of our models, the probability that the ith training sample equals 1, given our training features and our parameters, takes this form. Here we have Zi as the ith score, and the ith score is made by the intercept plus the ith feature vector times the vector of weights W. So that's what it is when y equals 1. When y equals minus 1, we're missing the numerator. Okay, so that's what we're given. And so how do we apply maximum likelihood? Well, we start with our likelihood like this. Always the first step is we assume that these labels, training labels Y, were independently generated, given X and our parameters. That allows us to rewrite this joint conditional PDF as a product of individual marginal conditional PDFs. That's always the first step. And now, second step, take the negative log of that. So we get a minus sign, and we find that when you take the log of this product, you get the sum of the log of the arguments. So we get that. And so now this is kind of the trickiest part of the derivation here. So now the problem is that we have this model stated here as a PMF, but what was given is not really a PMF, but it's like the probability of two different events. One event is that the label is 1. The other event is that the label is minus 1. So how can we write this PMF in terms of those two events? It's almost like we have to consider the two cases separately, the two possibilities of yi. Either it's 1 or minus 1. And in both cases, you get a different expression. And so we can do this little trick. You can think about it as one-hot coding, or you can think about it as what I call switching variables. But we're going to introduce these switching variables here. So notice that when yi is either 1 or minus 1, then this quantity, yi plus 1 over 2, is either 1 or 0. So what happens is, when yi equals 1, this guy comes alive, and this goes to 0, so this whole thing goes away. And when yi equals minus 1, then this one goes to 0, so that goes away, and this one turns into a 1. So that is how this log PDF is basically going to be either this or that, depending on whether yi is 1 or minus 1. It's a little trick. Is that making sense, what we did there? So we're trying to figure out how we can write these two different expressions in common and like this. And the trick is to introduce these switching variables. And in that case, when y equals 1, this log thing turns into here, or when yi equals minus 1, this thing turns into this. Okay. Making sense? Or anybody have any questions? That's the hard part. Everything else is just algebra. No questions about the switching variables? Okay. So basically now all we have to do is we have to plug in this expression here, and we plug in this expression here. Okay, so in the first case, we have to take the log of this. So the log of that fraction is log of the numerator minus log of the denominator. So log of the numerator is just going to be zi. And then we have minus log of the denominator. There's really no way to simplify that, so that's like there. And then over here, you have to do the same thing. We have log of the numerator, which is 1. That's a 0. And minus log of the denominator, which is here. So now all we have to do is multiply these out. So we have that fraction times z minus that fraction times this log. This is here. And then this times 0, nothing. And then we have this times this negative log. So we have essentially 1 times the negative log, which is here. And then we have this minus fraction times minus log, which is here. And the last step is to notice that this gets canceled by this. So we're just left with this expression. So here we have this is our negative log likelihood written as a sum in terms of all our training labels and all our scores. And the scores are the functions of our parameters and our features. Okay, so you could, of course, plug this in to here and here. It would get a little bit more complicated, but it's a little bit easier for our purposes to just sort of leave it separate. Okay, so at the end of the day, our objective is to somehow figure out what are the b and w parameters that minimize this function. So we're going to take a deep dive into this in Unit 6, next unit. But for now, we're going to exploit the fact that it turns out that this is a problem that's solvable, and scikit-learn solves it for us. So we're not going to get into all the details of how we do the optimization. We'll save those for later. But it's not a problem. We can do that. Okay, so once we do that, we're going to have our parameters b and w. And let's look at what happens when we do that on this simple data set. So this was our toy example where we have these guys that are clustered together. These are sort of separated. This is what happens with least squares linear regression. The regression line gets pulled to the right, and that means the threshold is also moved to the right, and this is not what we want to happen. So let's look at what happens with logistic regression now. Remember that we have this probabilistic model. The probability that y equals 1 given x, that's shown in the red line. So this is, once we fit the parameters b and w, we plugged them in. Now we can plot that probability. And you can see it smoothly changes from 0 to 1, depending on the value of x. And right here, when x is 5, that's exactly when the probability is 0.5. That would be the decision boundary, because we know that what we do is we basically look at that probability and threshold it. Equivalently, we can look at z and threshold z. Both are the same. So here you can see that we see that the y hat changes sign at 5, which is exactly what we would want on this data set. It's not bothered by the fact that that sample got pushed out to the right. It's not in the way that the least squares was. Okay. And you can also see here, essentially, that for these different samples, you can get a confidence on, how confident are you that the label was 1? So the further you get out to the right, you're more and more confident this label is 1. And as you get out to the left, you're more and more confident that the label was 0. Okay, so this is just to show that it is much more robust than least squares linear regression. Okay. Just a couple more things to finish up. So just to summarize, is what we just derived. So when the labels are 1 and minus 1, which is how we did the derivation, this is the expression that we derived. Here's our sum over all our training samples. Here's the scores ZI. The scores ZI are a function of the training features as well as our parameters. And we said we want to find the minimizers B and W that minimize this, and those are going to be our maximum likelihood parameters. If we would have redone this derivation for another very common choice of labels 0 and 1, you would find that a couple details change. Actually, the only detail change is that this turns into just yi. So sometimes when you look at one source or another, you might see this or you might see this. It's really just a matter of the choice that was made on how those training labels are coded. Okay, so here's a couple other things that happen in practice, though. Practice, you use this with regularization. We could use L2 regularization. We could use L1. So there actually is a very important reason we need regularization in this case. It turns out, if your training data is linearly separable, turns out that if you run this optimization without any regularization, your optimization algorithm will try to make your W parameters bigger and bigger and bigger. If it's an iterative algorithm, the parameters will just get larger and larger and larger the more iterations you let it. And if you let it go on forever, you go to infinity. And the reason why that happens is when the data is linearly separable, it turns out that yi and zi always have the same signs. So this quantity is always positive, and that means this is always negative. And it turns out that this quantity here will overwhelm this. So if you didn't have the 1 here, if you took the 1 away, this would just be zi. But because the 1 is in there, it makes this term a little weaker than this. And so if you allow it to, you'll just make the zi's larger and larger in magnitude, and this whole thing will just get more and more negative. And that's what happens without regularization. But if you put in just a tiny bit of regularization, so you can put this in for a tiny value of alpha, that's enough to prevent that from happening. Okay, so by default, sklearn includes this in the optimization, in its implementation. So you might then ask, well, how do we choose alpha? So, okay, if you want to avoid bias, because as we know, if you use a really large regularization strength, it squeezes your coefficients towards the origin, so you don't want to overdo it. Maybe you just want to use a tiny number for alpha to prevent this infinite solution. Or if you said, well, my features, I know that they're correlated. I know that ridge regression is good for dealing with correlation. It works in this case too. You might want to use a larger value of alpha. And in general, if you have the ability to do so computationally, you want to tune your alpha using k-fold cross-validation. That's the right way to find the best choice of alpha. If you don't have time and you don't want to worry about correlation, just choose a really small value of alpha. Okay, so again, another option is L1 regularization. As we know, the good thing about this is it can perform feature selection. It can perfectly turn off some of the W's. that could be useful depending on your application. But we also know that computationally, it's much more expensive than L2. So when you run this, you'll see that this is just quite a bit slower than this. So there's that cost as well. And in this case, too, of course, you want to choose alpha with cross-validation, ideally. So the very last thing is just to show you how it's done in scikit-learn. So it's this same library, the linear model library. Now you put in logistic regression. And it turns out that the regularization parameter is given in its inverse. So rather than specifying alpha, you actually specify 1 over alpha, which it calls C. So you want C to be big. Choosing C as 1e minus 1e5 is the same as choosing alpha as 1e minus 5. Okay, so that's how, I don't exactly know why for the linear regression they use alpha and for this one they use C, but that's what we're doing. So once you instantiate your model, here we're going to do some feature standardization, and then we'll just do our fit, logreg.fit. It computes all the B's and W's, and then we can do our logreg predict to get our predictions. And then if I want to see how often I'm correct, the accuracy, I create this binary vector, y hat equals y. So when it's correct, you get a 1. When it's not correct, you get a 0. And if you take the mean of that, that just gives you the average accuracy. So here, in this case, we got 96.9% accuracy for logistic regression with this choice of parameters, which is maybe not bad. Maybe you can do better. But the main point here is to see that it's pretty easy to do in scikit-learn, very similar to what you've done before. There's a whole bunch of parameters. We'll talk about those more a different day, but yeah, we'll talk about it more out of time for today. So please ask me some questions after class if you have any. Otherwise, see you guys on Wednesday.